So when you think about it, the internal moment, this term here, it equals to what? It equals to force P times Y, that's one moment, plus another moment, which is P times E. Would you agree? So they have two terms. That's P times E is basically the eccentricity effect. So we can take the summation of moment equilibrium, and depending on which direction you want to let it to be positive direction, but that, as you know, doesn't really matter. Suppose we say that clockwise is the positive direction. So in order to sum up everything, the moments we have, first one is P times E, that's positive, plus P times Y, minus M internal, must be 0. That's the moment equilibrium, which of course can be written as P times E plus Y minus M times internal to be 0. So that's the first step. That's the step 1. Found force equilibrium. And step 2, because we know that M internal equals to negative EI times Y double prime. And the original form is actually this, negative EI times the second order derivative of Y with respect to X. This is definition. And maybe after this example, just to clarify, because some students ask me the question during the break and even after class, and maybe we can come back to this definition to really explain why this definition is like this, in case some of you still are not clear about this. Now, because this M internal can be replaced by EI times Y double prime, so the original force equilibrium, we can just come back here, or we can just continue. Therefore, P times E plus Y, this will become plus, right? EI times Y double prime will be 0, right? Now, the way to arrive our governing equation is to keep everything related to Y at one end and everything else on the other end of the equation side, of the equal side. So we're going to keep everything related to Y on the left-hand side and everything not related to, not Y dependent, move it to the right-hand side of the equation, which means this. So this will, and then we're going to divide everything by EI, right? And that means what? That means this equation will become this. Then you're going to have Y double prime plus P over EI times Y, and this equals to negative P over EI times E, right? So this is just very simple. Move things around and divide everything by EI. Now, we're going to recall a very familiar definition. Since we already defined the buckling coefficient regular K, we already know that regular K squared is the ratio between P and EI. Then you can simply say that then we have arrived the governing equation, which is Y double prime plus K squared times Y equals negative K squared times E. So this is our governing equation, is this. And then what we have to do is to solve for it. Now, for a second order differential equation like this, we know that the complete equation, y of x, has two components, the complementary solution and the particular solution. So let's call one of them yc and the other one yp. Of course, you know that sometimes they go by different names, but you know that one corresponds to the case when the right-hand side of the governing equation is 0, and the particular solution corresponds to the case when it's not 0, which is, in this case, negative k squared times e. So what are these? Well, let's be clear. Complementary solution, and of course, you should know that this is also x-dependent, even so sometimes I don't show it, but they are always x-dependent. That reminds you that whatever you're going to write in the following must include the variable x. So it's a good habit to always write it yc of x. It will never give you something bad in return. We know that this equals to, there are two, usually complementary solutions consist of two harmonic components, and we associate with different coefficients. The first coefficient is a times kx plus b times cosine kx. This is a complementary solution. For the particular solution, it should be also x-dependent, but in this case, you're going to realize that in some cases, it may not be x-dependent. In this case, it's not. So this is just negative e. Now, if you recall differential equation, you know that if it's not x-dependent, you just have to divide everything by k squared. Then you can get a particular solution. That's just the short, some little trick you remember from differential equations. Then we have these two. So what we have to do is to figure out these two coefficients a and b. Once we figure out the values of a and b, then you have completely solved the problem. So far, we are not even talking about stability. So far, it's just differential equation and structure analysis. And step 4, so let's solve for it. Boundary conditions. The first one we know is when x is 0, y is 0. So this is basically to state the boundary condition at support A. So you can say that this is at support A, right? And we also know that at support B, what do we have? When x equals to capital L, there's also no deflection because at that end is a hinge. So there shouldn't be any deflection as well. That means y at x equals L is also 0. This means at support B. So where are the A and B's? This is how we define. Okay, and then we can just plug in. And this is the first example, so we can just put it in just as an exercise to get ourselves warmed up, right? So let's plug in. The complete solution is y of 0 equals to plug in x to be 0, right? So when sine 0, what's the value of sine 0?
0.
Sine 0 is 0, right? So we know that this is 0. 0, a times 0 plus b times 1, because cosine 0 is 1, right? Minus e must be 0. So from here, we know that the value of b is just e. Right? So this is what we found. That's actually found this condition. Now the second one, when we plug in x to be L, and you already know the value of b to be e, then you can just substitute e into b. So here we're going to write this. So it's going to be a times the sine KL. This is the first place that many students make mistakes. Sometimes they forgot. Sometimes they always put in 0. That's not 0. When you put x to be capital L, you have to remember every time when you write x, just replace it with L. Now this plus e times cosine KL minus e will be 0. So this is what? This is coming from the second boundary condition, right? And just simply by rearranging terms, the expression of A is, how do you find out the expression of A? How do you do that? First of all, move things from right-hand side to the left-hand side. For those which are not A dependent, move it to from the left-hand side to the right-hand side. So that includes these two terms. And then you divide everything by sine KL. So the expression of A is simply this. It's actually 1 minus cosine KL times E divided by sine KL, right? Just move things around, and that is our A. Now, once you have found the values of A and B, you already have the complete solution. And again, because it's the first example, so we're going to plug everything back, and you can see how the complete solution is. Or how does it look like? That means y of x is just the first term is A. It's a little bit tedious, but not that crazy. Times E divided by sine KL, this whole thing times sine KX. And you can do this. Plus E times cosine KX minus 1. To be, I'm sorry, of course not 0, right? That's it. So this is our complete solution. Now, you have realized that the first part in structural stability is the combination of structural analysis and differential equation, because this is the beginning of structural stability. Once we're right here, then we start solving it for stability problem. That's why I said differential equation, DFQ, and structural analysis are prerequisites, because we really need to use them extensively. Now we start solving the problem for stability. This will be page 21. And what is the step we have here? Step 4, all right? So it's a step 5. Starting with step 5. In step 5, the first thing we want to know is find the maximum deflection. So find Y maximum. Now in this case, where do you think that the maximum deflection would occur?